Okay, so we're given firstly a few true or false questions to test our understanding of the concepts in section 1.1. So the first one is we're given a linear system, and we're asked to verify whether the given statement is true or false. So that linear system cannot have a unique solution regardless of the value of k. Is that true or false? Right, so we look at two cases. If k is equal to 6, then that linear system becomes x minus y equals 3 and 2x minus 2y equals 6. And so from that we can we can deduce that x minus y is equal to 3. Okay, so if we look at that system, the system x minus y equals 3, that system has got infinitely many solutions. So the solution space of that system is the set S. Okay, so the set S is the set of all points where the x component is a parameter t, and the y component is a parameter t minus 3. And t is just a real number. And it is clear that we can make t any real number, and that this point here will always satisfy that linear system. So we've got infinitely many solutions in that case. So obviously for that particular case there are no unique solutions. There are no unique solutions. So next we need to consider the case where k is not equal to 6 to complete the argument. Right, so considering the case where k is not equal to 6, then we have the linear system as it is there. Right, so we can just go and rewrite that linear system so that it's a little bit neater. Right, so basically from 1 and 2, we can then equate 1 and 2 together. And so from this side here, we've got x minus y, which we know there is equal to 3. And then from this side here, we've got equality there. And that is all equal to k over 2. And then from there, it implies that k over 2 is equal to 3. Right, so from there, we have that k is equal to 6, which is a contradiction. Okay, so we're contradicting that statement there. We assumed that k is not equal to 6. Right, so the system has no solutions when k is not equal to 6. So when k is equal to 6, we've got infinitely many solutions. If k is not equal to 6, we have absolutely no solutions. So there are no unique solutions. So therefore, the answer to the question is true. Okay, so the statement is true. That linear system has no unique solutions regardless of the value of k. All right, so the second question asks us, is this true or false? If the number of unknowns in a linear system exceeds the number of equations, then the system must be consistent. Okay, is that true or false? Okay, it seems that this statement, it feels like it generally cannot be true. So if I want to show that a statement is false, I need to provide a counterexample. So I need to provide an example where the statement isn't true. So to show that that isn't true, the statement, if a number of unknowns in a linear system exceeds the number of equations, then the system must be consistent. So I need to provide an example where the number of unknowns in the linear system exceeds the number of equations, and I need to show that this system is then not consistent. Okay, so let us consider that system. That is a system of two equations and three unknowns. So the number of unknowns exceed the number of equations. Now we can view each one of those equations as a plane in R3 space. The first one is the plane z equals 1, and the second plane is the plane z equals minus 1. And so we can answer the question. So in that system, we've got clearly those two planes don't intersect one another. So I can never find a point x, y, z that lies on the plane in the equation 1 and on the plane in equation 2. So that system is clearly inconsistent. So there I've generated an example of where we've got an equation, a linear system where the number of unknowns exceed the number of equations, and the system happens to be inconsistent. So as I said, there are two linear systems with three unknowns, and the system has no solutions. Right, so that statement is false. Now, if we were to just quickly look at a diagram to illustrate question 2, there we've got R3 and we've got the point 0, 0, 1 and the point 0, 0, minus 1. So remember that this is the coordinate system with x the first value, y the second value, and z the third value. And if we look at the plane z equals 1, it is the plane that goes through that point there. And if we look at the plane z equals minus 1, it is the plane that goes through that point there. Right, and upon inspection, you can clearly see those two planes don't intersect anywhere. So there are no points x, y, and z that lie on both those surfaces. So that's an inconsistent linear system, and it's a linear system with more unknowns than equations. Right, so the next question here is the statement true or false. Let's look at the statement. If each equation in a consistent linear system is multiplied through by a constant c, then all the solutions to the new system can be obtained by simply multiplying the solutions from the original system by c. Now, is this true? And my feeling again is that quite possibly this statement is most probably not in general true. Right, so let's pick a linear system that's got m equations and we've got n unknowns. And it's a linear system with real coefficients. All right, so all these numbers here, all these numbers, they're real numbers. Okay, right. And we pick this linear system firstly to have a solution, and we pick it so that at least one of these numbers here is non-zero. And I mean, you can easily construct such a linear system which has got exactly one solution. And let's, for argument's sake, assume without loss of generality that this first B1 is a non-zero number. Now, if we look at this system, let us also assume that this system has a solution, and the solution is given by these values, okay, S1, S2 up until Sn. And as I said, that is a solution to the linear system. Now let's see what happens if we multiply this whole linear system with a constant c, and we also multiply each one of the solutions, or the solution to each variable, we multiply them all by c, and then see what happens. So there we multiply each equation through by constant c, and we multiply the solution of each variable with c. Alright, so what we're doing now is, let us assume that these values are in fact, or this point is a solution to my to the system above, which is this system here. So if I plug them into my original system, every single equation will be satisfied, right? So we're going to first replace the x1s, and we're going to replace them with the solution for x1, right? So we're going to replace them with these values here. And then we're going to do the same for the x2s. We're going to replace them with the solution value for x2. And that is going to be this. So we're going to replace that. Okay, and then we're going to carry through. We're going to do up until right at the end. And we're going to replace the xn's with the solution value for xn. Okay, and that we got there. Okay, and remember we assume this is a solution, so it should, if I plug this point in, it should satisfy all my equations. Okay. Right, so again, simplifying that, we get that linear system, which is still the same linear system. Alright, so further simplifying that, we get the linear, that still the same linear system. And remember we said this S1, S2, up until Sn, that's a solution to my original linear system. Okay, and that translates into what we have here. Alright, so there we've got c squared times b1 equals to c times b1. And remember we said that this is a linear system where b1 is not equal to 0. Okay, so that implies the only way that can be true is if c squared minus c b1 is equal to 0, which happens only when c squared minus c is equal to 0, and that happens only when c is equal to 0 or c is equal to 1. Alright, so if we take c to be any real number except 0 or 1, then it is clear that if I multiply the solution of the old system with this c, and I get a new set of points, this set of points is definitely not going to be a solution to the new system. If c is any number except 0 and 1. Right, so I will not generate any solutions to my new system by simply taking the solution of the old system and multiplying it with c. So saying that in words, basically, it is clear that if C is any real number except 0, 1, then multiplying the solution of the old system with C doesn't generate any solution to the new system. So you can certainly not generate all the solutions of the to the new system. We cannot generate any. So that statement is clearly it's false. Right, so the next question, is it true or false the linear system with a corresponding augmented matrix is consistent? Is that true or false? That's pretty easy to see. So if we look at the augmented matrix corresponds to this linear system. It corresponds to the linear system 2x minus y equals 4, 0x plus 0y equals minus 1. Now on inspection you can see there's clearly no point xy that lies on both 1 and 2. No such point exists. Right, so, I mean, this is obvious. Any point that lies on 1, if you plug it into 2, it's never going to satisfy 2. Right, so this system is inconsistent. Right, so the answer to the question is it's not consistent. It's inconsistent, so it's false. Right, so the next question is solve the following system of equations. So again, we've got 3 equations with 3 unknowns, and we're asked to solve this system. So I'm going to solve it via or setting up an augmented matrix and then using that to solve this linear system. Right, so there we've got our right, so writing that system down, we've got 2x plus 0y plus 2z equals 1. Okay. And we've got 3x minus y plus 4z equals 7. We've got 6x plus y minus z equals 0. Right, setting up the linear system of equations, we get the augmented system. So there we've got that part there. Alright, so the first column is going to be, there we go, that's the first column. The second column is going to be there's the second column. And the last column is going to be okay. And that is going to be my augmented matrix. Right, let's change the first row by multiplying through by a half. Let's just make it a little bit simpler. I prefer to work with ones. So dividing by 2 the first row, we get first entry becomes 1. Then the third entry becomes 1, and the final entry becomes 1 over 2. Okay. Now the next thing that I'm going to do, I'm going to change the third row by multiplying through by a third. So the first entry is going to become, right, so it's going to become 1 minus a third, 4 over 3, and 7 over 3. And then I'm going to change the last row by multiplying through by 1 over 6. So the first entry is going to become 1. The second entry is going to become 1 over 6. The third entry is going to become minus 1 over 6, and the last entry is going to be 0. Then I'm going to change the second row by adding negative the first row to the second row. Right, so multiplying the first row by minus 1, we get that. And then I'm going to add it to the second row. So the second row, the first entry becomes minus 1 plus 1, which is 0. The second entry in the second row stays minus a third because it's 0 minus a third. The third entry becomes minus 1 plus 4 over 3, which is going to be a third. The last entry is 7 over 3 plus minus a half, which is 11 over 6, right? Then I'm going to change the third row by adding negative the first row to the third row. So multiplying minus 1 through the first row, we get that in red, and we're going to add it to the last row. So minus 1 plus 1 is going to be 0. 0 plus 1 over 6 is 1 over 6. And minus 1 plus minus 1 over 6 is going to be minus 7 over 6. Right, so that is going to be replaced by minus 7 over 6. And the last one is going to be 0 minus a half, which is minus a half. It's always good to write down these calculations so that you can keep track of exactly what it is that you're doing. It's very easy to make mistakes with these things, so it's always good to write it down in a step-by-step way. So I'm going to change the second row by multiplying through with 3. So basically multiplying through by 3, we're going to get the first non-zero entry is going to be minus 1. The second or the last the entry in the third column, that entry is going to be become 1. And 11 over 6 is going to become 11 over 2. Then I'm going to change the last row by multiplying through with 6. So basically the first non-zero entry is going to become 1. The second, this last entry is going to be minus 7. And the entry in the last column is going to become. Then I'm going to change the third row by adding the second row to the third row. So we're going to get here, this entry here is going to become 1 plus minus 1, which is going to be 0. Then the next entry is going to be 1 plus minus 7, which is going to be minus 6. And this last entry is going to be 11 over 2 minus 3. And that is 5 over 2. Alright, and so we're going to change just one more. We're going to change the third row by multiplying through with negative 1 over 6. And so this entry is going to become, it's going to become 1, and we're going to have that the last entry is going to be 5 over 2 multiplied by minus 1 over 6, which is minus 5 over 12. It's going to be minus 5 over 12. Okay, so it's minus 5 over 12. Right, just quickly change the second row by multiplying through with minus 1. Okay. Right, so that's going to be plus 1 minus 1 minus 11 over 2. And then what I'm going to do is I'm going to now change the second row by adding the third row to the second row. Right, so this entry is going to become 0, and then I'm going to add minus 11 over 2 to minus 5 over 12. And so that's going to become minus 71 over 12. Right, then I'm going to change the first row, and I'm going to do that by, again, adding negative the third row to it. Okay, so negative the third row is going to become minus 1 and 5 over 12. Okay, and now adding that to the first row, minus 1 plus 1, that entry there is going to become 0. Okay, and then I'm going to add 5 over 12 to a half, and that is going to give me 11 over 12. Right, so now I've manipulated my system, and I've reached a point where I can merely go and read off the actual solution. And if we take this new system and we check to which linear system this corresponds to, you're going to easily see the following. From there, it follows then that this corresponds to the system 1x plus 0, y plus 0z is equal to 11 over 12. The second row corresponds to 0x plus 1y plus 0z is equal to minus 71 over 12. And the last row corresponds to 0x plus 0y plus 8 is equal to minus 5 over 12. Right, so that is the solution. Now, I did this very slowly, and I'm going to assume from here on end that you guys are already familiar with this type of manipulation, which we will discuss in a little bit more detail in section 1.2, but I assume now that you should already now know how to manipulate matrices with your three row operations, which we discussed as multiplying a row with a constant, or you can add one multiple of one row to another. And we also looked at switching rows around, which is your third type of operation. We didn't switch any rows around in this case, but take note that there's a third operation that we didn't use. Right, question 6 asks us to consider the following system of equations. So you've got three equations, three unknowns, and you're asked to show that in order for this system to be consistent, we need A and B and C to satisfy C is equal to A plus B. All right, so this is a straightforward manipulation question. So we're going to start off by first constructing the augmented matrix of the system. All right, so there we've got this linear system here. So let's go and construct the augmented matrix of the system. Okay, so writing that down, we get 1x plus 1y plus 2z equals A, 1x plus 0y plus 1z equals B, and 2x plus 1y plus 3z equals C. Okay, constructing the augmented matrix, we take that side there. We take there our first column. We take our second column there. Take our third column there. And that is my augmented matrix. Right, so there's my augmented matrix. So what I'm going to do is I'm going to change the second row by adding negative the first row to the second row. So remember, you always write the row that you change, you write that first in this notation here. Okay, so we're changing the second row. So let's multiply the first row with -1 and add that to the second row. Right, so multiplying the first row through by -1, we get -1, -1, -2, and -a, and let's add that to the second row. Right, so we're going to add that to the second row. So the first entry in the second row is going to become 0, because you're adding -1 to 1. So that's 0. The second entry in the second row is going to become -1, and the third entry is going to be -2 plus 1, which is -1. And the last entry is going to be -a plus b, and that is going to be b minus a. Okay, now we're going to change the third row by adding -2 times the first row to the third row. Okay, multiplying -2 through the first row, we get -2, -2, -4, and -2a. Now adding that to the third row, the first entry in the third row is going to be -2 plus 2, which is going to be 0. The second entry is -2 plus 1, which is going to be -1. And the third entry is going to be -4 plus 3, which is going to be -1. And then the last entry is going to be C plus -2a, which is C minus 2a. Right, next we're going to change the third row by adding negative the second row to the third row. Right, so we multiply the second row through by -1, so we get 1, 1, and a minus b. And now we're going to add that to the third row. So 1 plus -1 is obviously going to be 0. And then again 1 plus -1, again that is going to be 0. And then in the last instance, we're going to get C minus 2a plus a minus b. Right, so that is going to be okay. Right, so simplifying, we get the last row, 0, 0, 0, C minus A minus B. Okay, let's, for cosmetic purposes, just change the first row by adding the second row to the first row. Okay, so that basically means that the second entry of the first row is going to become 1 plus -1, which is going to be 0. The third entry is going to become -1 plus 2, which is going to be 1. And the last entry is going to be basically b minus a plus a, and that is then basically going to be, it's going to become b, all right? And then lastly, multiplying through the second row, we're changing it by multiplying it through with -1. That is then going to be, that's going to become +1, that's going to become +1, and basically then we've got a minus b. Okay. Right, so there's my there's my linear system. Okay, so right, so basically if C if C minus A minus B, if that is not 0, then basically then the last row is going to correspond. It's going to correspond to the equation 0x plus 0y plus 0z is equal to a number C minus A minus B, which is not 0. Okay. But the left-hand side is always 0, and no 0 number can equal a non-zero number. That's going to imply the system is inconsistent. All right, and in that case, the system will be inconsistent. Okay, so what happens if C minus A minus B is 0? Then C is equal to A plus B. Basically our system becomes x plus z equals b, y plus z equals to a minus b. Right, so the solution space becomes, so it's basically all points. We can set the variable z equals to a real number. We parameterize it. So let's parameterize z as t. So then we can solve for x as b minus t. We can solve y as a minus b minus t. And we have the variable z, which is equal to t. So basically the solution space is all points where t is a parameter and t is a real number. Okay, so it's all points where the x component is b minus t, the y component is a minus b minus t, and the z component is t. And so in this case, the system is consistent because it has a solution set. Okay, so question 7 asks us to basically prove that if these two linear equations have the same solution set, then the two equations must be identical. What does it mean for two linear equations to have the same solution set? It means that any solution to the one equation is a solution to the other equation and vice versa. All right, so they have the same solution set. And we need to now show these two linear equations are exactly the same. Right, so let's take my two linear equations, 1 and 2. Now, to make things easier, I've just relabeled x1 as y, and I've relabeled x2 as x. So it's still the same two linear equations. Right, so now note that it is clear that this point 0c lies on equation 1. If I make x 0 and I make y c, then the left-hand side is equal to the right-hand side. So 0c is definitely in the solution space of equation 1. Now, as 1 and 2, remember we originally assumed, because they both have the same solution set, we have that the point 0c will also lie on equation 2. So whence from 2, if we go and plug 0c in there, I make x 0 and I make y c, then what do I get? I get c plus 0 equals d, and that is going to imply that c is equal to d. So I proved basically that these two quantities are the same. Right, so we proved that c is equal to d. So now let's take another point on equation 1. Let's take the point where x is equal to 1 and y is equal to y prime. We can easily find such a point. We just plug in x equals 1 and we solve for what y needs to be for the point to lie on equation 1. Now, because equation 1 and equation 2, they both have the same solution set, means any solution to equation 1 is also a solution to equation 2. So therefore this point 1 y prime will also lie on equation 2. Alright, so as I said previously, if you take this point here and you go and plug it into your first equation, you get this equation here, obviously. Okay, and as I said, as 1 and 2 have the same solution set, this 1y prime lies on 2 as well. Thus, in 2, if you make x equals 1 and y equal y prime, you get y prime plus L is equal to d. Now recall that we said c is equal to d. Right, so basically remember we said that c is equal to d. So basically this equation here we're going to take, and we said c is equal to d. Okay, so that equation is going to be equal to that equation. Right, so that is then going to imply that we have this, okay, and basically that is going to then imply that k is equal to L. Alright, so we have now proved that k is equal to L and c is equal to d. So that implies the two linear equations, are identical.